What are arithmetic circuits, by the way? What do you understand by the term arithmetic circuits? You've seen the slides. The slides were already put online. How many of you have seen the slides, by the way? I've been putting them online in advance, but how many of you have seen them? You can just raise your hand and I will know. Okay, so out of 40, around 6 people have. 15%, 7 people. 15% of the class, let us say. Okay, not bad. So what are arithmetic circuits? At least you should be able to respond.
So for performing arithmetic operations, we need adders and subtractors, all these things. So these are the arithmetic circuits.
Good. And when we talk of these adders and subtractors and multipliers, what is the most important thing that we need to be looking for?
So one thing is the logically correct circuit. Other thing is that we need to make sure that in a fixed amount of delays we get some output. For example, if the carry is propagating over the adders, then it should be coming in some defined worst case delay, and that should be the most critical part of it.
And you want to reduce that worst case delay. It's not just that you delay time, but it's also that you want to reduce that worst case delay. Am I right?
Yes, sir.
Okay. So Dipanshi, I see your hand raised. Did you raise it when I asked about the slides, or do you have a question?
No, sir, about the slides.
Okay, so you can lower your hand. Just give me a minute. Sure. So arithmetic circuits are very commonly used wherever you have a processor. For example, this is a typical or a very top level view of a processor where you would have some data paths and a memory, inputs and outputs, and a control part. And in this data path, you will have, for example, what is called as adders, multipliers, shifters, comparators, etc. All of that. The control part would have finite state machines, counters, and so these are the different components that you will see in this digital processor, let us say. Memories and interconnects with arbitration units and buses and switches and so on. So in this lecture, we are intending to spend time on arithmetic circuits. In the next lecture, we will be spending time on memory circuits. Okay. Again, this is just a top level glimpse. This is by no way an intent to make you an expert on adders or multipliers or even memories. If you want to learn more about memories, I would suggest take up the memory design course in the next semester. For adders, multipliers, take up a capstone project or another project like that, where you can study more about them and design them if you wish to. So that would be a preferred mode of learning more about arithmetic circuits in terms of adders, multipliers, and the like. Okay. So a typical data path, so for example, if I say that there is a 64-bit processor, or here I have shown a 4-bit processor. So a typical data path is, so if I say there are 64 bits in a processor, then what could be done? It could be that a bit would enter over here. There is a 32-bit adder here. There is a 32-bit multiplier here. So the bit would go all like this. A circuit just bit, any bit can take, any word can take. But that is not really optimal. So what is typically done is that data paths are designed as bit slices. So over here, you will have, let us say, A0, B0 going in, and that will result in the output B0, O0, let us put it as O0. Okay. The next slice would have A1 and B1 going in, and the final output would be O1. So they are organized and arranged in such a way that data flow is kind of streamlined. It's fast. It doesn't waste time in neither interconnects or other stuff. And In your data path, that is how you include registers and adders and multipliers and shifters and everything there. If some particular function is not required on a data, that particular block is simply skipped, bypassed, and you run out. Okay. So a slightly complex stuff, would mean that in addition to just multiplexers and shifters, you could actually have adders implemented also in stages. In the sense that if you look at the previous slide, we said adder is one stage, shifter is another stage. However, in this slide, what I'm saying is that an adder, just so that you have a fast addition possible, may be split into multiple stages. And you may have one stage of adder over here, second stage, and third stage as you move on. But they're all in terms of bit slices only. This is bit slice 0, this is bit slice 1, and the like. Are you able to see this? Any questions still here?
Sir, is it just to enable more parallelism, right?
Anyway, if you have to add 32 bits, you have to add 32 bits. So there has to be some parallelism in there. We will, as we look into the adders, just iske baad adders hi shuru hoga. When we will start to look into the adders, you will see what I mean by adder stage 1, adder stage 2, and adder stage 3. We will talk about tree adders, and that is where this concept will become more evident. But yeah, you're in a data path, you're processing all the different bits in parallel. There could be interconnects between them. For example, we showed that if you notice over here, we are showing that there is some output from bit 0 going to some other bit, some output from bit 0 going to another bit somewhere in the data path. So there could be some such interconnects also. Okay. But they are running in parallel. Largely they are running in parallel. Okay.
And sir, what is this loopback bus?
This is information going back saying that, okay, there is an overflow or there is, so system level bus it is, which would give information to close any loops that were there. Okay, now addition is completed, so you can accept the next input. It could be ready signals, it could be those things.
Okay.
Sir?
Yes.
So what are shifters?
What are shifters? Shifters are shift registers, where the number of clock cycles you give, it will just rotate like barrel shifters, they will just rotate the word in there.
So shifter could be used to manage the pipeline stages, right? Means if we give serial input and we take parallelly output, so anything like that?
Shifter is a set of flip-flops. So in those terms, you can think of using them as a scan chain also. Yes, no problem with that. But shifters, barrel shifters are not just for pipeline. Barrel shifters are barrel shifters, which could be a part of, say, multiplication and division also.
Yes, sir.
Ranjit?
Sir, so basically this bit slice represents the complete data path, right, sir?
Yes, for one bit.
But sir, how can we just be sure that in a particular architecture, the data path for, suppose if you have n bit slices, then all the n bit slices are identical. It's not very...
They may not be. They may not be. यहाँ देखो ना, हमने क्या करा? In this case itself, we've taken bit 0 का output of adder stage 1, and we have merged it or taken it as an input to, let us say, bit slice 7.
Okay.
Then in the second wiring stage, we've taken the output of bit 0 into something like bit 55. So need not be. We're not saying they are symmetrical. What we are saying is data path is in one flow.
Okay.
This is just to streamline so that when you design, you do not also have errors, end up with errors because of some confusion or interconnects. Because when we will see just a little while later, tree adders, you will see there are so complex interconnects that it's better to separate it like this.
Okay, sir.
Okay. Rajneesh?
Sir, in the previous slide, in the bit slice design,
Mhm.
a separate register was given in a bit slide. But in this one, in this diagram, there is no separate register means in the bit slice.
Yeah, so if you look at the previous slide, they were adding that register to latch the incoming data. That's fine. There are two different architectures. They would these guys would in the second bit slice over here, possibly they're already saying that this is coming from a register file, is it not?
Here it has considered it as a common one earlier.
Yeah, it is coming from a register file already, so you do not need to register it again.
Yes, sir. And one more thing, sir. Sir, you in this you said that this bit slices of 1 bit, but sir, in previous slide, it is a 4-bit bit slice.
No, this is a bit slice.
Oh, okay, sir. Okay. Yes.
Okay.
Yes.
Yeah. Okay. Anything else?
Sir, just a clarification, sir. If I have a bit slice, let's say if it is a very simple circuit of a mux. So in a bit slice, we can say that output of many bit slices can converge into a single one. Like in a multiplexer, many inputs are there. There is only one output.
Not necessary, Gagandeep. It could be that I have 4 inputs coming for every multiplexer, and those 4 inputs are available separately for all the bits. And I select just one out of those. Happens, no? So it could happen that let us say my data path is, just for the sake of area, I kept the data path at 16 bits, but my total words were 64 bits. Now there is a data path of 16 bits, but my overall word width is 64. So what would I do? I would organize my words in such a way that words 0 to 15 are processed in the first cycle, then word 16 to 31 are processed in the second cycle, then word 32 to 47 are processed in the third cycle, and so on.
Paging kind of thing.
Paging, yes, could be. But there could be more than one inputs coming to the multiplexer at the level of the multiplexer, which then is converged into one, and then the entire shifter, adder, stage 1, etc. goes on.
Okay.